What if the biggest breakthrough in AI wasn't more data or more GPUs, but a completely new way of connecting intelligence itself? Welcome to this deep dive into Manifold-Constrained Hyper-Connections, or mHC. For nearly a decade, ResNets and transformers have relied on the same residual design. Today, we explore a fundamental architectural shift, one that CryptoMinds actively tracks, teaches, and applies in real-world AI systems. The AI industry is hitting a breaking point. Training smarter models now demands exponentially more compute, memory, and power. Costs have crossed hundreds of millions of dollars, locking innovation behind massive infrastructure. At CryptoMinds, we see this not as a scaling problem, but as an architectural one. Hyperconnections introduced a radical idea. Instead of endlessly stacking layers, expand the residual stream itself. More pathways, more expressive power. And crucially, no increase in flops. This decouples intelligence capacity from raw compute, a principle we emphasize in advanced AI architecture training. But innovation without discipline breaks fast. Unconstrained hyperconnections shattered the identity mapping that keeps deep networks stable. Signals exploded. Gradients vanished. In large-scale models, gains surged to nearly 3,000, making reliable training impossible. This is exactly where theory must meet engineering rigor. The breakthrough is manifold-constrained hyperconnections. By projecting connections onto the Birkhoff polytope, the system enforces a doubly stochastic structure. Every layer becomes a convex combination of features, preserving signal norms and restoring stability. This is geometry solving a systems problem. The results are striking. Unconstrained architectures behave chaotically. mHC stays perfectly conditioned, even across 60 layers. Forward and backward gains remain tightly bounded around 1. This is not a marginal improvement. It's a 3 orders of magnitude stabilization. And this stability translates directly into performance. Across 3 billion, 9 billion, and 27 billion parameter models, mHC consistently outperforms the baseline. At CryptoMinds, this validates a core belief. Smarter design beats brute force scaling, every time. A breakthrough architecture still needs real-world efficiency. DeepSeek engineered kernel fusion, mixed precision processing with tile-lang, and selective recomputation to break the memory wall. The result? Only a 6.7% training overhead. This is systems-level AI engineering done right. When DeepSeek R1 launched in early 2025, the industry felt it immediately. This wasn't just a new model, it was proof that focused teams, armed with the right architecture, could challenge compute-heavy incumbents. At CryptoMinds, we help teams build exactly this kind of leverage. Markets reacted fast. NVIDIA's valuation dropped by nearly $600 billion. Why? Because this work questioned a dangerous assumption, that more chips automatically means smarter AI. Architecture had re-entered the conversation. This is a redefinition of AI economics. DeepSeek achieved comparable performance to $100 million models for just $6 million, roughly 6% of the cost. It's a masterclass in efficiency, strategy, and architectural intelligence. Manifold-constrained hyperconnections mark a new foundation for AI. By restoring identity mapping through principled geometry, mHC opens the door to topological innovation beyond brute force scaling. At CryptoMinds, this is exactly where we operate, training teams, advising leaders, and building systems where architecture becomes the competitive advantage.